Hey guys, Henry here with a little redneck engineering project for you today. So for those of you that watch my channel, or if you've seen some of my videos before, you'll know that I started saddle hunting last year. Before I was using the climber stand, and now I switched over to the saddle, which I really like it. It's got a lot of good advantages. It's lighter to pack in. It's pretty cool. I use like a rope system, so I just loop my rope up in the tree and I climb up with the rope, so I don't use sticks or platform or anything. I do have a little ring of steps that I put in a backpack, but I don't carry a platform or any sticks out there. So it's nice and light. It's really comfortable. I always feel like when I was sitting in the climber stand, I always felt like I was going to fall out. I'm not afraid of heights, but they're not really my favorite either. So I always just kind of felt a little like unstable and insecure, but with the saddle, I'm like tied right into the tree. So I actually feel a lot more comfortable in the saddle, from like the falling out perspective. So that's really nice. And I think it's easier to shoot out of the saddle too, probably just because of the comfort level. I don't feel like I'm gonna, fall over, so I can focus on shooting. But one thing I have noticed though is what a lot of guys complain about. It is called hip pinch, which basically, just to kind of show you what that is so like if you're looking at my saddle here, here, let me flip this around. There we go. So if you're looking at my saddle, I'm wearing it. It's kind of pretty simple system. It's just this thing that you wear, and then you got this, which is called your bridge. And when I climb up, I tether myself to the tree with a tether line, and this holds on like this. So if you look, the sides of this bridge is basically, taking all the tension from your tether. There's an angle there. So what that's doing is it's basically pushing in on both of my hips. So that's what they call hip pinch. And on a long sit for a long time, that can kind of start to get a little uncomfortable. So what I want to do is, I work as an engineer, and we do a lot of projects like modularized stuff where we do lifting. Like we'll design like a skid or something that has equipment on it, and they will lift this up in the air and put it on a truck and then take it to the site and then lift it off the truck again. And what we do a lot of times with that is they'll use a spreader beam. So what the idea is, here, just bear with me 1 second and I'll show you. Okay, so the idea of the spreader beam is that you put it kind of in between the two hoist points, and now instead of having this sharp angle here, you've got the angle up here, but then your cable or your whatever, in this case, my loops on my saddle, they basically become straight. So what that does is it gets rid of, in our case, we have like these lifting lugs, which is like a plate of steel with a hole through it. We don't want those to bend. So if the force is kind of straight on, or right in the same plane as the plate, there's no bending there. Whereas if it's at an angle, it's going to cause that plate to want to bend. So this is advantageous to have this like this. So I think that this is going to help because it's going to direct that force instead of being, pressing in on my hips. It's basically just going to press outwards now. But how that does that, this beam in between, spreader beam, or in this case I just kind of mocked this up right now with a piece of cardboard tubing, is going to go into compression. So we got to figure out what the force in there is going to be, and then obviously I'm not going to do this with a piece of cardboard, but I made this mock-up because I want to do the same thing but with a piece of PVC pipe, because PVC is it's not metal obviously, so it's not going to clink and clank and make noise, but it's pretty strong and it's pretty light. So I think that it's going to be a good material choice. So I'm thinking a PVC pipe probably close to dimensions of this will probably be okay. But let's figure it out just to make sure. So what I kind of did is sort of modeled their system here a little bit. So I took some dimensions here. My little mock-up piece of pipe is going to be this guy. and I measured that, or I cut that to be 15 inches. And then I measured my two pieces of the two sides of my bridge, and they were about 8.5 inches each. So this is like my system. But I don't know what these angles are going to be. So I know that by symmetry that these two angles are going to be the same. So I put X there, and then, just Y up here for this other one that we don't know. So I'm going to use what's called this law of cosines, which says basically an extension of the Pythagorean theorem. And that says that side C squared equals side A squared plus side B squared minus 2 times A times B times the cosine of the angle between side A and B, which in this case is one of our x's. So I'm just going to go ahead and rock that formula out, and I come up with that x is 28 degrees. So then we know the other x, obviously, they're the same, and then we just got to figure out the y, which is pretty easy. All the interior angles of a triangle always add up to 180, so 180 minus 2x gives us that the y is 124 degrees. So now we kind of know the geometry of our system. So, excuse me. What I want to do now is basically model our thing with the forces on here. And I'm going to do this as a plane truss. So obviously this is very simplified, you know what I mean? Like this isn't like a roof truss for a building or something, but the same principles are going to apply. So we can use some really basic static formulas to figure this out. So I'm going to assume, well, first of all, our first assumption with plane truss is that everything is acting in a plane. So, there's nothing, no forces coming into or out of the page. It's all, in this plane. And then the second assumption is that each of these members, so in this case, we have some cables here, and this is actually going to be a solid member, but it doesn't really matter. They all work the same. Except for a cable can't take compression. But in this case, we have a solid member there, so that's okay. We're going to consider them all pinned at the ends, which means that you're not going to have any bending moment or any cross forces coming across these items. No shear, basically. So they can only take axial load. So they can only be, along the axis of the member. They can only be in tension or something like this. I know those arrows are kind of small to see. Compression. So just by looking at this, I can tell that because we have, this tension coming up here, and I'll get to these forces in a second. This tension up here, I know that these two members are going to be in tension, and that this member, by equilibrium, is then going to have to be in compression. But we'll figure, I'll show you how that all works out. So, I'm going to say that my tension, this is basically where my tether rope attaches, right? So I'm going to assume that this is 200 pounds. And that's a pretty hefty assumption, because I normally stand on a ring of steps, so most of the weight is actually going to be going through my feet. But I'm figuring, okay, I weigh about 165 pounds. If I add on some boots, maybe a heavy jacket, my gear, all that stuff, maybe I'll be about 200. Like I said, most of that weight's going to be going through my feet, so this rope really isn't going to be holding 200, but this will kind of give us a safety margin for things like if I slip off the platform or impact loading or stuff like that. So when I'm moving around. Or another thing too is, this whole thing is based on this perfect symmetry assumption. Well, if these angles change, these forces change. So, if this is asymmetric, there might be more force on this side or something. So, let's just roll with a 200. And like I said, these loads are going to be pretty small for the strength of a PVC pipe. So I think it's okay to be pretty conservative here. So I've written down here that my tension is 200 and my reaction force, this is basically what's going into the loops of my saddle, is 100 pounds on each side. So, kind of from inspection we can see that, because we know that we have 200 pounds going this way, and we know that the sum of the forces in all directions has to be 0. So the sum of these two forces must be 200. And by symmetry, you can kind of just look at it and realize, pretty quickly that the force is going to be split evenly. Whereas if this was over here, then these forces wouldn't be equal. They would be, one would be larger than the other. But another way that you can quickly prove that is in addition to having all the forces be equal, all the moments must be equal. So if I take a moment about this point, this force will go away because it's through the moment, so or through the rotation point, so there's no moment arm. And you would quickly see that the moment arm between force A, which, you kind of extend this out here, this moment arm from here to here is exactly 1/2 of the moment arm from here to here. So for all the moments to be equal, this force must be exactly half of what that tension is. So that's just kind of, you can just prove that to yourself, or if this wasn't symmetric, there's a way to figure that out. But okay, so moving on. The next thing we're going to do is we're going to use what's called the method of joints. So we've got our 200 pounds of tension, and then we have these two are the two tensile forces, or I guess we don't really know if they're tensile or compressive, but we're pretty sure that they're going to be tension, right? In our two sides of our bridge. And again, symmetry is going to help us out here. So we hit 124 degrees. So we know that this is going to be 62 on this side and 62 on this side. So, and also by default, then the two forces must equal each other, right? Because the angle is the same. So we know that F1 equals F2. So let's just focus on F1 for now. So if we sum up our, I've got my little axes over here. If we sum our forces in the y direction, we will find that F1 times the cosine of 62 degrees equals 200 by 2. Why by 2? Because we just said that F1 and F2 are equal to each other. So rather than writing F2 in here and having a factor of 2, I just divide the 100 by 2. Because we know that each force is going to contribute half. So 200 divided by the 2 gives us 100. So we just go ahead and crank that math out, come out with F1 equals 213 pounds. And that's positive, so we know that that's in tension, which is what we thought. So then, let's go ahead and do joint B. I actually made a mistake here. So similarly, let's check our y direction. So, well, here, we got the force 2 that we just found from our last joint is 213. And then we have this force. I'm assuming that this is in compression. Like I said, I kind of know that that's going to be compression already. So I drew it facing negative. And this is 28 degrees. This was our 62 degrees. And this is the 100-pound reaction force. So if we sum our forces in the y, we basically end up with what we had last time. 213 times cos of 62 equals 100, which checks out. So that basically tells us that we did the first step right. So we haven't made a mistake so far, so that's good. And then next, let's sum our forces in the x direction. So I have, because positive x we considered this direction, this 213 is negative. So negative cosine 28. And then F3, the way I've drawn it, because I already kind of know that it's going to be in compression, is also negative x. So minus F3 equals 0. So you go ahead and you crank this whole thing out, and you end up with that F3 equals negative 188 pounds, or 188 pounds in compression, which is kind of what we, or exactly what we had surmised from our first sketch over here. So I think we're on the right track so far. Okay, so what do we want to do next? Well, we basically have this member now, and we know that it's got 188 pounds of compression that basically works on both sides, right? Because this member has to be in equilibrium too. So what we're going to do is, instead of looking at this horizontally, let's flip things a little bit and look at it like this. Think of it like a column. So now we have a column that's pinned at both ends. So we can use column theory to figure out some more information about this. Excuse me. So what I'm going to use next is called the Euler column buckling critical loads. So Euler came up with this equation here. This is kind of another view of our pipe with our compression coming in on both sides. And this, with the 2 pins at both ends, this becomes the formula here. The critical load equals pi squared times E times I over L over 2, where L is the length. So here, what I want to do, I'm going to throw a little bit more safety on here because we don't really know what P critical is. So, well, it's 188. But we're going to knock it up a little bit with a safety factor of 1.6. And the reason why I'm doing that is because for ASCE, American Society of Civil Engineers, they have a whole bunch of different like load combinations where you basically like factor up the loads. So what we'll do is we're going to factor this up a little bit by a factor of 1.6. So basically increase the load by 60% because it's a live load. And 1.6 is the live load factor. So you crank that out quickly, you find out this is about 300 pounds, 301. So what about this E in this I? That's kind of our next question here in this equation. So E is a material property. It is the Young's modulus of the material. So it has nothing to do with our problem in particular, or the geometry of the pipe, or anything that we're looking at. It's a material property. So they test these. ASTM, which is American Society of Testing Materials, tests all kinds of materials, and they do all kinds of different tests on them, and they publish results. So you basically just go online, or look in the ASTM books or whatever, and you find a value for this. So what Young's modulus is basically telling you, if you have, what they do is they do a stress strain test. So they measure, they basically put load on something and they measure how much it deforms. And if you have, oops, sorry, my bad. So if you're looking at stress versus strain, most materials, almost all materials, will have some point where they behave in a what we call a linear elastic range, where there's this is a steady slope here. It's not like a curve going either way. It's a slope that you can measure, and it's a straight line. So the slope of this line is what E is. And then usually, at some point things will start to, they get out of the linear elastic range and become inelastic. But we're just, talking about the linear elastic range here for E. So that's basically the slope of this. But like I said, we don't have to figure all that out. Somebody else figured that out for us. And it is 490,000 PSI, pounds per square inch. So basically what that means is it takes, for 1 square inch, if you had a 1 square inch bar of this stuff, you would need to load it up with 490,000 pounds to be able to get that thing to like start linearly elastically deforming. So that's what we're going to do. Then, seems how we know this, we're going to plug this into our Euler formula. So we had our critical load, pi squared, and then we got our E that we know. I put I required because we don't know what I is going to be. And then here's our length squared, 15 inches squared. So I come up with I required equals 0.014 inch to the fourth. That's the units for this. So by this point, you're probably saying, what the hell is I? I is the moment of inertia of the cross section. So if we look at our pipe like this now, in section view, and we imagine like a pair of axes, parallel axes here, we would end up with something. Well, I don't have the picture. Okay. But we would have something that looks like this, right? Here's your pipe, and then, here's your axes here. Let me show you, right? So, we can call this Y and this X. So what I basically tells you is it's a geometric property. So E, the Young's modulus, was a material property, had nothing to do with the geometry of the problem. I is kind of like the opposite. It has nothing to do at all with the material, and everything to do with what the geometry of the section is. So with E and I together, it totally describes that pipe. One term describes the geometry, one term describes the material. So I is basically just its force resistance about those axes, basically how much resistance to rotation about that axis that it has. So if we're talking about like by our axis system here, if I turn this like this, it'll have, it would take some amount of, of force to make this, or moment, to make this thing want to rotate in this plane or in this plane. And because it's, obviously a tube, it's a circle, it's symmetric, so they actually happen to be the same for both of these. But if you had something, like what people call an I-beam, or what we usually call a W, or a wide flange section, something like this, you'll have much stronger, a much higher I value in this axis than this axis. But because this is a pipe and it's symmetric, we don't have to worry about that. They're the same. So that helps us out a lot. So what we're going to do is this formula here, again, you can kind of just look these up. They're all over the internet. This is the moment of inertia formula for a round pipe. So the I value is equal to pi divided by 64 times big D time minus, big D to the fourth minus little d to the fourth. So this is your outer diameter, this is your inner diameter. And they have these formulas for all kinds, every different type of shape that you could imagine. They're all over the place, so it's easy, you just look it up. So you could find this for square, solid bars, solid pipes, I-beam sections, channel sections, everywhere. There's, formulas for this stuff. So you just go ahead and look that up. So for now, I'm going to assume that we're going to have a 1/4 inch thick wall. So the difference basically between big D and little d here is going to be essentially, would that be a 1/2 inch? Because 1/4 plus 1/4 is 1/2, right? So I'm going to say, let's try a 1 inch pipe. Now the way they do pipe sizing is, it's a little hard to see on this example because it's a really thin wall pipe. But basically when they size pipe, when you buy pipe at the store, you're buying it based on what they call a nominal size. So that would be like for water pipes and stuff, they're measuring the inner diameter. So if I say I'm going to buy a 1 inch pipe, the inner diameter is going to be close to an inch. It actually won't probably be exactly an inch. It'll be like something stupid, like, maybe 15 16ths or something like that. Like it'll be kind of some odd size, but we use the nominal size usually. So the point here though is that would basically refer to, when I say I'm going to buy a 1 inch pipe, that would be the small d, and then the large D would be, that nominal size plus 2 of whatever the wall thickness is. So if I got a 1 inch pipe, I'm going to have an inner diameter of 1 and an outer diameter, assuming that we have a 1/4 inch thickness, is going to be 1/4 plus 1/4, which is the 1/2, 1 1/2. So go ahead and I punch all this out, and I come up with my I for that particular pipe would be 0.199, or roughly like 0.2. So that is obviously a lot larger than our 0.014 that we came up with. Again, like I kind of said in the beginning, PVC is pretty strong, so, and 188 pounds really isn't a whole ton of force on it, or even I guess we factored it up to 300. So like we're way over designed on this, but that's good because we kind of considered this whole thing like a static system, right? And that's really not going to be the case. Like I said, when this moves around, the forces are going to fluctuate, and if there's any type of like shock or impact loading, we kind of have this expression of like a force applied over an infinitesimally small time is infinite magnitude, which basically that means like if you have like a quick, like an impulse force, like a drop or something like that, the way that kind of propagates itself, you end up getting like a localized force that maybe only lasts, a fraction of a second or something, but it's much larger than like what the static load would be. But I think we have plenty of safety built into this thing. We're basically like a factor of 10 higher than we really need to be here. So we're looking pretty good. So I'm going to go ahead and go shopping for a pipe and see if I can't pick up like a 1 inch or something like that PVC pipe, and then we'll go ahead and build this thing up. All right, guys, thanks for watching.